When I start routing a board like this, the most important thing to understand is that the routing is not where the design actually happens. The real work was already done during the floor planning stage. If the floor plan is good, the routing almost feels automatic. If the floor plan is bad, no amount of clever routing will save you. So the very first thing I route is the USB-C CC pins. These are simple signals, but they are a perfect example of why placement matters. Because the CC resistors were placed directly above the CC pins on the connector, this routing is trivial. I can drop vias right next to the pads and connect the CC pins to their pull-down resistors with essentially zero trace length. No awkward bends, no crossings, no wasted space. This is exactly what a good floor plan buys you. Instead of fighting the layout, you are just executing it. Next, I route the PRO-G pin from the charger IC to its pull-down resistor. This is a small detail electrically, but it is conceptually important. That resistor value directly defines the charging current of the battery. One resistor decides how hard we are pushing current into the cell. Because of that, I want this connection to be clean, short, and unambiguous. Again, because the resistor was placed deliberately close to the IC, the routing is short and direct. There is no guessing and no compromise. The schematic intent is preserved perfectly in the layout. After that, I connect the STA-T pin to the LEDs. This is another area where good placement completely removes complexity. The LEDs and their series resistors were grouped together intentionally, so routing the STA-T pin to both LED paths is straightforward. There is no spaghetti routing and no backtracking. The traces are short, clean, and easy to follow, which matters not only electrically but also when someone else looks at the board later and tries to understand what is going on. Once the critical signal routing is done, I move on to power, starting with the 5-volt input on the top layer. Instead of routing this as individual traces, I draw a polygon pour for the 5-volt rail. This immediately reduces impedance and saves space. The polygon naturally wraps around the charger IC, the input decoupling capacitors, and the series resistor for one of the LEDs. Because the decoupling capacitors were placed correctly during floor planning, they land directly inside the 5-volt copper area, exactly where they should be. There is no need for long traces or awkward jogs. The copper itself becomes the connection. Then I do the same thing for the output side. I draw a polygon for the battery output voltage. This polygon connects the charger IC output, the output decoupling capacitors, and the custom charging pad that I created for the battery. This is a great example of how layout and mechanical decisions overlap.